Alright, new chapter, time to learn a whole bunch of new stuff. There are quite a few topics introduced in this chapter, so let's go through each one of them a step at a time. So we've already worked with the set of all real numbers and the set of integers, but we're also introducing here the set of natural numbers and the set of rational numbers. So the set of natural numbers are basically counting numbers. They don't include negative numbers. The set of rational numbers are ratios, so like 1/2 or -17/4 or 3/1. Remember that with rational numbers, if you divide the numerator by the denominator, you get something with an ending decimal point. So the irrational numbers are the ones like the square root of 2, where you'd get some sort of really long answer and the decimals go off forever. We have our set of all real numbers, which is basically everything that we can come up with besides anything imaginary, like the square root of -4. And then we have the set of integers, which are whole numbers, positive, negative, and 0. We can also further restrict these sets to include only the positive real numbers, or the real numbers that are greater than or equal to 0. Same with our rational numbers and our integers. Take note that the set of non-negative integers is the same as the set of natural numbers. So for this chapter, we'll be working with sets and operations on sets. So remember that sets are usually defined with a capital letter, and we can either specify all of the elements of the domain if we have a small amount of items, or if we have something like the set of all positive integers, we're going to need an equation for it, which we will cover later with set builder notation. We will also be working with the universal set and the empty set. When defining a problem and specifying sets, we must also include the universal set U, which the other sets are contained within. So, the elements of all of the sets we're working with must also be in U. If we look at some combinations of sets together, it's possible that the result will be an empty set, and so we'll denote that with the null symbol. So let's look at an example with some sets. We have two sets, A and B. A has 1, 2, and 3 as its elements, and B has 2, 3, and 4 as its elements. And then our universal set is 1, 2, 3, 4, and 5. So, which elements do A and B have in common? The elements that they have in common are 2 and 3. So this is known as the intersection of A and B, which would be denoted in this way. Next, which elements does A have that B doesn't have? And which elements does B have that A doesn't have? A has the element 1 and B does not. This is known as the difference of A and B, denoted in this way. B has 4 and A doesn't have that one, so this is the difference between B and A, which is denoted in this other way. What is the set if we combine all elements of A and B? Combining A and B gives us the set 1, 2, 3, and 4. This is known as the union of A and B, which is denoted in this way. What is the complement of A? In other words, what numbers are in the universal set that are not also in A? The complement of A here would be a set that contains 4 and 5. This is A's complement, and we write it as A prime. So let's summarize this really quick. The intersection of A and B are the elements that are common to both A and B and nothing else. So if A has some elements that B doesn't have, those aren't included in the result. Think of the symbol between A and B kind of like an N for intersection. The union of A and B are all elements that are either in set A or in set B, or both. So think of that union, U, when thinking of both of them together. The difference of A and B, if we have A minus B, would be the elements in A, which are not in B. And the complement of A, which would be written as A prime, are the elements of the universal set, which are not in A. We can also represent these graphically as Venn diagrams. When drawing a Venn diagram, make sure to also enclose your diagram in a box, which is the universe, or the universal set. Again, A intersection B is only the elements that they have in common. A union B are all of the elements that they have together. A minus B is A without any of the elements of B. And A complement is everything in the universe with the exception of whatever is in A. We will also be talking about subsets of a set. So using this notation, we can say that A is a subset of B, which means that every element of A is also an element in B. We can also write this formally as, for every x, if x is in A, then x is also in B. We can also say that A is equal to B, and this essentially means that A is a subset of B, and B is a subset of A. So now let's look at 4 sets. We have the original A and B, 1, 2, 3 in A, 2, 3, 4 in B, but now we have C and D. C has the elements 1 and 2, and D has the elements 3 and 4. We have the same universal set as before. So, is C a subset of A, and is it a subset of B? Is D a subset of A, and is D a subset of B? So the results are that C is a subset of A, all of C's elements are also in A. C is not a subset of B because C has the number 1, but B does not. So we'll write it with the other notation, which is the subset of, but with a slash through it. D is not a subset of A, and D is a subset of B. So if C is a subset of A, is A also a subset of C? No, because A has the element 3 and C does not. They are only subsets of each other if they are equal. Okay, finally for this section, we're going to cover set builder notation. So with sets, if we have something like the set of all even numbers, we can't write out every element in the set. So we need to use set builder notation to define what that set is. There are 2 different ways to describe our sets. There's the property description and the form description. So we'll cover both of these. So for the set of all even integers, we're going to say that x, some element x, is some even integer. So first we have to say that x is an integer. X belongs to the set of all integers. Then we define what x is, and again, similar to in chapter 2, we say x is equal to 2y. X is equal to 2 times some other integer. Now we also have to say that y is an integer in this set builder notation, so we also have to say for some y in the set of z. So we're explicitly defining that x is an integer and y is an integer, and that x is some even integer because it is 2 times some other integer. With the form description, rather than saying we have some element x and describing the properties of x, we're going to say that any element of the set is of the form 2 times y, so the definition of an even integer, and that means we also have to define the set that y belongs to, and y is an integer, it belongs to the set of integers. So this one is a more concise reading, where you kind of have the equation on the left side and you define the set on the right side. So this was a lot of information for one section. Let's work through some examples to kind of solidify that knowledge. Okay, so let's look at these sets. I've just put letters in them, they don't have to be numbers per se. So we have our universal set from A to G, we have A, B, and C, so we have to find each of these. Let's look at A intersection C. So remember that this is whatever they both have in common. So A and C, we have, well, just D in common, right? this is equal to just D. Okay, what about A union C? This will be equal to both of their elements. So we have B, we have C, we have D in both of them, but there's no reason, if we have two D's, it's the same as just having one D. We don't need to rewrite it. E and F. So that's that set. As a quick note, if we have B, B as a set, and then we have B as a set by itself, these are equal. Just having duplicates doesn't matter. Some sets might have duplicates, and it's just the same as having it that one time. Okay, so let's look at C prime. C prime is going to be everything that's in the universe that is not in C. So we have A and B in the universe, but we're going to skip whatever is shared with C. So C, D, E, F, not in there, and then we'll have G. So that's C prime. Let's look at the difference between B and C. So what does B have that is not in C? So that will be A and B. So we're just removing that C. And then how about C intersection B prime? Well, first let's look at B prime. B prime is going to be D through G. So D, F, or D, E, F, and G. So that's B prime. What is in common between C and B prime? Well, we'll have D is shared, E and F are shared. So here we have D, E, F, G, here we have C, D, E, F. Whatever's in common is used in the intersection, and that's our solution. Alright, let's look at some subsets. We have the same universe, but now we have a different set of sets. So is A subset of B, or is it not a subset of B? Well, all of the elements of A are in B, so we will use this symbol to be the subset of B. Is B the subset of C? Well, all of the elements of B are in C, so we'll use the same symbol, subset of. Is C a subset of D? Well, they actually have nothing in common, so we're going to write this with a slash through it. Is D a subset of the universe? Well, our universe should include everything that's in these sets, so yes. Okay, how about C prime? So C prime is going to be everything in the universe that's not also in C. So we're going to skip over A, B, and C. We'll have D, E, F, and G. So is C a subset, is C prime a subset of D? Yes, and actually they're equal to each other. So since these are equal, I'll just put an equal sign. Is B a subset of A? Well, no, B does not. B has more elements than A does, so even though A is a subset of B, B is not a subset of A. So we'll say no. D prime, is that a subset of C? So let's say D prime is equal to, let's look at this. We'll just skip these in the universal set. We'll have A, B, and C. So actually they're equal. Just like this one here, C prime is equal to D, D prime is equal to C. Okay, and then down here we have the union of B and F, so B and F. So let's say B union F is going to be equal to the elements in B and the elements in F, which is just a C. Is this a subset of C? Those are equal. So the intersection of the union of B and F is equal to C. We'll also have questions like this in the book where we have a universal set, and then we have A, B, and C, and then it asks to prove whether they're equal or not. So let's first look at the union of B and C. So B and C is going to be 1, 2, 3, 4, 1, 2, 5, 6, 10. So 1, 2, 3, 4, 5, 6, and 10. Okay? And then what is the intersection of A and this part? So the intersection will be whatever they have in common. So we'll have 1 and 3 and 5. So A does not have a 2, so we're just not including the 2, and we're not including any of the other numbers out there. So this is what this part's equal to. Let's look at the other side. What is A intersection B? This is equal to 1 and 3. That's all they have in common. What is the intersection of A and C? That is 1 and 5. That's all that they have in common. So if we take the union of both of these, then we're going to get the set 1 and 3 and 5. So these are equal to each other. Okay, down here we have the complement of A union B. So A union B is going to be them both combined. So 1, 2, 3, 4, and 5. And then the complement is going to be whatever's in the universal set that is not in these. So those numbers. 6, 7, 8, 9, 10. And now we need to look at A complement intersection B complement. So A complement is going to be 2, 4, 6, 7, 8, 9, 10. That's a little bit messy. Let's kind of maybe put this over here. A complement. So 2, 4, 6, 7, 8, 9, and 10. B complement is going to be 5 through 10. So 5, 6, 7, 8, 9, and 10. Okay, so these complements, the intersection of what they both have in common, will be not 2, not 4, not 5, but we'll have 6, 7, 8, 9, and 10. So these will be equal. 6, 7, 8, 9, and 10. And so those are equal. Okay, let me erase a little bit of this so we have some more room to work. A intersection the union of A and B. So, do we have that written up there? I probably had that before. We have the union of A and B. We'll keep that. Now, what is the intersection of A and A union B? So, obviously this is going to be whatever A has in common with this, which will just be the set A. So this whole thing, A has 1, 3, and 5 in common with that intersection, so it's essentially just erasing the B altogether. So these are equal. Finally, let's look at converting the property description to the form description in our set builder notation. So here we have X is some element of a set. X is an integer and X is even, so again this is the set of all even integers. So for our form description, rather than talking in terms of X, this first part's just going to be how, basically the equation to get what that element would be. So let's say it is 2 times some integer, but then we also have to explicitly specify that k is an integer, so we have to say that it belongs in the set Z. So here's the equation, here is the set that k belongs to. We're essentially saying x is equal to 2k, and we're putting this as part of the form, and we, again, have to explicitly specify that k is an integer. Over here, x exists in Z, it's an integer, x is odd, so remember we have x can be 2k plus 1 as an odd, the definition of an odd integer. So we'll use that as our formula part, and again, explicitly specify that k is an integer, otherwise our whole definition of odd isn't going to work out. So this is the form description of that. Now down here we have x is twice a perfect square. I forgot the curly brace on this side. But we also have that x is some natural number, so x is equal to 2 times some square. So here's our perfect square. If it's a perfect square, that means k is going to be a integer as well. So otherwise, I mean, you can say 2.5 squared is something, but we're talking in terms of perfect squares, so integers. So our formula will be 2k squared. And again, k has to be an integer, or in this case, we'll do a natural number. So we'll say that. And so this will be the form notation.